up and running on the live stream, so whatever. Years.
Okay, can you hear me in the back? Great. I have the absolute pleasure to introduce Dr. Janice Bytheway. When I first met her, she said, yes, my last name is a prepositional phrase, and I've never forgotten that since. We actually met 19 and a half years ago at an REU in Norman, Oklahoma. And so for those doing internships, keep tabs of those friendships and people, because you never know what you're going to end up. We were just joking the other day that we really started precip extreme forecasting because our REU apartment we got put in was leaking every time it rained, and so we had to get really good at forecasting to like put out the bowls to collect all the rainwater. Anyway, that's another story. But we fell in love with storm chasing together. We both followed each other to Colorado and continued storm chasing and doing a little work too. And I'm not going to share all of her journey because it's a really fascinating one, but currently she works, I wrote down all the acronyms, the Hydrology Applications Division of the Physical Sciences Lab at NOAA. So that's where she is currently, based out of Boulder. She's going to talk to us about how we modernize understanding and predicting precipitation extremes. So Janice, go ahead and take it away.
Thanks. Okay, Mike, good, yes, okay, cool. So starting out, I just want to really quickly, there's a lot of co-authors here, so very quickly acknowledge them. Most of us also in Boulder at NOAA, but Jimmy and Sarah working with us at the Weather Prediction Center in College Park, Maryland. So as Ange mentioned, I wanted to take a couple minutes to start and sort of, you all are going into your future, so here's how I got to here, besides on a plane yesterday. So I grew up in Wilkes-Barre, Pennsylvania, which is kind of like right there in northeastern Pennsylvania. And the big event that I always heard about growing up was the Hurricane Agnes, the flood of 1972, talked about it all the time. My parents told stories about it. The house I grew up in, I heard about how they had to remodel it for the flood. So that was really my first, yes, this is very interesting. Floods are interesting. And then in 1997, the movie Twister came out. And even though I was always interested in weather, it wasn't until this movie that I knew that I found out that you didn't have to be a weatherman, right? You didn't have to just be the guy on TV. Research meteorology was a thing. And I admit to running around in khaki pants and tank tops and button-down shirts for years in high school. After that was my high school uniform. And so after high school, I went to California University of Pennsylvania, which is in a town of California in the state of Pennsylvania. So here's where I grew up, right, in Wilkes-Barre. CalU is over here, kind of, about 30 miles south of Pittsburgh, where I fell in love with Pittsburgh sports teams. It was the farthest I could go from home while still getting in-state tuition. Small school, right? You've never heard of it except Marissa, who went to Millersville. So very small school, not a lot of students. My class was 18 people. But what it afforded me was a lot of individual attention and a lot of opportunities to do a lot of things. So we had a 2-week field course in the summertime. So I actually took storm chasing as a class. Saw my first tornado as a class. We went to, we had an AMS local chapter. We went to conferences, which really got us sort of, exposed to research. And then as Angela mentioned, I was able to do the CASA REU program, which took me to Norman, Oklahoma, where I really kind of was like, yes, research is what I want to do. So after that, went to Colorado State for my master's, and my master's research was working on satellite precipitation. It was more in the algorithm development sort of realm though, and I did not love that. And I did not love, I didn't really feel super confident in my ability to ask the right questions and do the research. So after that, I took, actually took 4 years between my master's and my PhD, and I worked on 2 separate NASA measures projects. One doing a precipitation climate data record, and one doing the National Water Vapor Project, the NVAP-M climate model or climate data set of local water vapor. And then after that, I was like, okay, I guess I feel pretty good about research now and confident in myself. So I went back, did my PhD, which was in model evaluation of forecast of extreme precipitation. After that, I got hired at CERES, so the Cooperative Institute for Research in Environmental Sciences, but I sat at the NOAA Physical Sciences Laboratory, so I've actually been at the Physical Sciences Laboratory for about 7 years. I was hired for this Advanced Quantitative Precipitation Information Project, which was looking to improve forecasts and observations of precipitation in the California Bay Area, and then also got involved in the study of precipitation, the lower atmosphere and surface for hydrometeorology, or SPLASH field campaign, which just wrapped up outside of Crested View. And then in 2021, Congress passed the Bipartisan Infrastructure Bill, which provided NOAA with some additional funding, which is how I wound up in a NOAA federal position starting earlier this year. So that's kind of my professional journey. And then my fun fact is I don't just study the water, I kind of like live in it. So in my spare time, I am a volunteer first responder with the Larimer County Dive Rescue Team, which I am like huge into swift water, which means flash flooding. So when we had a flash flood a couple of years ago, I actually got to go and help pull this car out of the river, which was super fun and exciting. And then this is just myself and my husband. My cat, he's black and yellow. His name is Pittsburgh, because that's the color of all the Pittsburgh sports teams. That's my dog Timber, and that's a few of our additional pets. My husband and I raise bees for fun. So getting into the science, I'm going to start and talk about probable maximum precipitation, what it is, why we need to update this data set. So probable maximum precipitation is used in dam design and operation and updating them. We have over 92,000 dams in the United States, spread all over the place, used for water management, used for flood control, and a lot of these dams are considered high hazard dams. High hazard dams just means if they fail, loss of life is going to happen. One loss of life, that makes it a high hazard dam. So we have a lot of those. When these dams were designed, or no, actually going back to that, why do they fail? Overtopping is the most, kind of frequent way that they fail. You get too much precipitation in the basin above the dam, too much water comes down over the top, starts to erode the dam structure, and they fail. And so probable maximum precipitation is what we use to kind of design these, right? So we want to know what's the maximum depth of precipitation that can possibly fall in that basin of the dam. What do we have to design the dam to make sure it can withstand as much rain as can possibly fall? So it's kind of how much rain can actually fall in a given area in a given duration. And so it's, it's kind of a theoretical value of physically possible precipitation. And it's, again, used for high hazard dams. Nuclear facilities also use PMP to run and operate and design their facilities as well. So PMP desperately needs updated, though. So you can see here, the current estimates we have are kind of piecemeal, right? There's different estimates for different parts of the country, and you'll see here we've highlighted that they're like, the newest one is from 1999. We've made a lot of advances in scientific estimates and forecasts of precipitation since 1999, and the oldest ones are from the 50s and 60s, right? So these are 50 to 60-year-old estimates of precipitation. The other reason these are so old is there's really been a lack of financial support to do this. Some states, so these are kind of the national estimates, but some states, for example, Colorado and New Mexico in the last few years have gotten together, funded their own updates to probable maximum precipitation data and estimates. And so some of the other states have actually also done sort of private company having them update PMP for them. But NOAA now is going to do like a larger scale one. So as I mentioned, science has advanced. Some recent events have actually exceeded what we thought PMP was. So Hurricane Harvey exceeded the PMP for Texas. But more often than not, PMP is considered to be too high. And so we're telling the engineers, you have to build your dams to this standard. That might not actually be the standard they need to build to. Current PMP, it doesn't account for any uncertainty, so it's a deterministic, this is the value you get, this is what you have to build to, and it doesn't account for any climate change. The climate has changed a lot since 1963 in some areas. And so the infrastructure risk is really becoming a lot higher stakes as these get older and older.
And these are, just to clarify,
Sure.
these are estimates for those whole areas together, or like different basins within each of those areas? or-
You know, I haven't actually looked at the hydrometeorological reports. I think they're for, they would be for, they're like a spatial, like a map. So the PMP, you know, in the mountains of California versus the Central Valley is different, but they were just all created at the same time. Yep. So, as I mentioned in my introduction, in 2021, the Bipartisan Infrastructure Law was passed, as well as the Precip Act. So, BIL provides NOAA support now. Now we have money to modernize PMP, to do it for the entire CONUS, to do it in a robust way that is going to account for climate change and include uncertainty estimates. And then the Precip Act, which was passed in December of 2022, actually mandates that we update PMP estimates now no less than every 10 years. So we're not going to go 50, 60 years again before we update these numbers. And the first step to this is to fund NOAA to work with the National Academies of Science, Engineering, and Medicine to convene an ad hoc committee, which is going to consider different approaches. So these people are going to look at the state of the science of PMP, and then they are going to come back and provide recommendations to NOAA on the best way to go forward and do this. Because there's a lot of different ways you can calculate PMP. So the National Academy study kicked off in October of 2022, and it's going to take until June of next year to complete. We have 12 volunteer experts, we have state climatologists, we have statisticians, we have modelers, we have hydrologists. It's a really great committee, super smart people, big names on it. We've had 4 public information gatherings, so if you're interested and you want to look further, you can look at the National Academy's website. It's here at the bottom of the screen, and you can watch the recordings of these 4 public information gathering sessions that they've had, where so they've talked about you know, what data do we need, periods of records, resolutions, etc. In this one, they actually had people from FEMA, the Army Corps of Engineers, dam safety organizations come and tell them what they need. What do we need to know from PMP to run and update our facilities? Had one on modeling extreme precipitation and climate modeling of extreme precipitation. And then the most recent one that they had last month was looking into potential contributions of AI and machine learning that might be useful for the updated estimates. So we're waiting for this NASEM study, right? So the National Academies is going to tell us what to do, but we're supposed to start working on things now. And so while we're sort of working with them and waiting for them to come up with their recommendations, we're just really sort of pursuing different research to look into different tools. And one of the things we're really focusing on are our modeling capabilities that we have. And so what we really want to look into is using numerical modeling more comprehensively. And so obviously numerical models are nice. They are continuous in space and time. They can be high resolution. You know, they're physically based, so you don't have to make a ton of assumptions about things. Very, very beneficial in data sparse regions. You can run ensembles, you can get estimates of uncertainty. And another bipartisan infrastructure law project that is also at the Physical Sciences Lab with us is actually to create next generation hydrologic models. And so us being here, working on PMP, getting our new estimates of extreme precipitation, we'll be able to integrate that with that next generation hydrologic modeling project as well. And so some of the things that we've been kind of looking at, I mentioned the Colorado, New Mexico updated PMP. For that project, they ran the high resolution rapid refresh, so our operational HER model, and they just took like all of the forecasts at all of the hours, and they layered valid times on top of each other to create a huge super ensemble of HER forecasts. And that was kind of how they did their PMP work for that project. We've been kind of dabbling in looking at how different numerical cores are representing extreme precipitation. So this is just an example. The MPAS from NCAR forecast versus a model using the FV3 dynamical core, looking at maximum precipitation from those. And finally, what else can be mined? Like what do we have right now that we can start digging into and see how we're representing extreme precipitation while we wait for the National Academies to finish their report. And so NOAA has several high-resolution operational products that give us precipitation estimates, and we also have high-resolution precipitation models. And so that brings us to Chapter 2, which is looking at the HREF, which is the High-Resolution Ensemble Forecast System. So the HREF, it's a 10-member, it's called an ensemble of opportunity. So most ensembles, you have one model, you run it with different initial conditions, or you run it with different boundary conditions to get your ensemble. Here, these are just 5 different models altogether. So we have 5 convection allowing models, and then we take and time lag them as well. So, so you can see the HER and then a 6-hour lagged HER. So you just take the HER that was run 6 hours and use forecast hours 6 through 12 instead of forecast hour 1 through 6, for example. So HER, here we have the HRW, which stands for high res window. Sorry. I've got one thing in one hand and one thing in the other hand. We'll use the actual pointer. So high resolution window, so this is ARW, this is basically like your WRF advanced research model. We have a high res window FV3 model. We have an NSSL model that's being run, and then the NAM CONUS NEST. And you might recognize the HER and the NAM. These are operational deterministic models that get used pretty frequently as well. And so you can also see in this table that they have, different microphysics, different boundary conditions, different boundary layer models, different vertical levels. They all have about the same horizontal resolution, so 3 or 3.2 kilometers. These are all post-processed to the same 3-kilometer grid before I get my hands on them, which is nice. They're run twice a day, so up to 48 hours. Once you get to that 48-hour forecast, you kind of lose that HER lag because they're only a 6-hour forecast. But 48-hour forecasts, hourly output, run twice a day. It's run at 0 and 12 UTC. We've got 10 members. We've got 48-hour forecast. I'm only looking at 0Z forecast. It's a lot of data. So to sort of manage our compute resources, just looking at the 0 UTC runs here. The post-process products, so like your ensemble means and your probability match means, those are all 5-kilometer approximately grid spacing. But as I mentioned, the individual members are all at 3 kilometers. And of course, the individual members get run more frequently, but the twice a day is when they're put together in the HREF. You want to have consistent model configuration over time, right? If you want to look at a model, you don't want them to change the things they're doing. And so this has been running in this same configuration with no updates to the individual models since May of 2021. And that gives us 3 full years in which to study extreme precipitation. We're just going to focus on the warm season here. And so we have some different science questions that we're interested in. What does extreme precipitation look like in the HREF? My colleague Diana Stovern is going to look at how skillful the ensemble means are in capturing the warm season precipitation. Sarah Troniak is going to look at how often the HREF predicts high probabilities of extreme precipitation. So when does the HREF predict, say, a 50% probability of 3 inches in 6 hours? How often does that happen? And then that leaves the ones with no names after them, which are what I'm going to talk about today. So what does extreme precipitation look like in the HREF? How well does it predict extreme precipitation at different thresholds and different accumulation periods? And how do the individual members contribute to those forecasts of extreme precipitation, right? We have all these individual members. Which ones are contributing to our extremes? And this is also going to give us a little bit of information, as I mentioned, about our deterministic operational models that we're using as well. So question 1, what does extreme precipitation look like in the HREF? So we're going to look, when I said different thresholds and accumulation periods, our accumulation periods that I'm going to focus on in this talk are going to be 1, 6, and 24 hours. And so here are our ensemble maxima for those 3 time periods. Maybe not so surprisingly, that for summertime our ensemble maximum is in the southeastern United States, where our tropical cyclones are centered. As you get into your 6 and 24 hours, you can see that like the off the charts extremes sort of move up into the Mississippi Valley and the Central Plains when we have those MCSs that are a little bit slower moving. Extreme precipitation, And you also start to notice at 6 and 24 that some of them, they start going kind of up the Atlantic coastline as well, probably also most likely a result of tropical cyclones. Of course, in the western U.S., not as much heavy precipitation, but you'll notice here in Southern California and Nevada, there's this 6-hourly and 24-hour, it's not the highest maximum that we're seeing, but there's some pretty heavy precipitation that has been predicted by this ensemble in Southern California and Nevada, and that's, if you did not have 2023 in here, you would not see that. So this is the effects of Hurricane Hillary here, which is actually, without 2023 and without that event, we wouldn't see that the model could actually predict these extremes in that region. Because particularly on the West Coast, most of their heavy precipitation is in the wintertime. Okay, so this is looking at CDFs of ensemble maximum precipitation. So cone is wide here on the left, right? And not surprisingly, our hourly, maximum precipitation tops out at about 150 millimeters an hour. That's still 6 inches-ish in an hour. That's a lot of rain. There's not as big a difference between the 6 and 24 hour. Those are kind of a little bit more of the same mechanisms that are going to produce those types of storms. But you can still see that our 6 hourly precipitation is going to top out at about 12 inches. That's a lot. Like, I live in the desert. That's kind of unfathomable to me. And then for daily, our 99.9-ish is that 12 inches, but it goes beyond that. As if looking at 10 different ensemble members at 3 different accumulation periods was not enough, I also divided this out into regions because different things are causing the extreme precipitation in different regions, right? In the Mountain West, we have monsoonal precipitation, we have MCSs and fronts, and our tropical cyclones. So divvying this out into different regions to see how the HREF is predicting precipitation in these regions. And not surprisingly, given the previous slide, the Southeast really has a lot of heavy precipitation. So now at daily time scales, we're maxing out at about 500 millimeters per day in the Southeast. The middle of the country, the Northeast, these are all fairly similar, about the same. And then you see the West Coast, not surprisingly, has the lowest hourly ensemble maximum precipitation. But then again, when you get into 6 and 24 hour, you see it's kind of hard to follow that gray line. But at daily, it actually exceeds the maximum in all the other regions besides the Southeast. And again, as I mentioned, if you take away 2023, you can see now that our 6 hourly and daily West Coast precipitation is much lower. And so looking at these extremes where your N, right, your frequency of occurrence on this is already very low, it only takes one event to really change your statistics that you're seeing. This is just looking at which member gives you the most frequent maximum rainfall. And so different colors for the different models here on the bottom. This is all rainfall greater than 0. We've thought about adding some sort of threshold because given this is particularly at hourly, this might just be the member that makes it rain the most often. But you can kind of see, so the most frequent maximum member at hourly precipitation, this almost looks like a topographic map, right? This green and purple sort of follows the highest terrain through the Rocky Mountains, where that's the NSSL and the NAM, producing the most frequent maximum precipitation there. And then it kind of does the same too, right, in the Appalachians going up. And then sort of in the Great Basin, you have HER and the lagged HER, and then the lagged NAM really over most of the eastern U.S. And you can see that as you go to longer accumulation periods, that NSSL model really starts to take over in the western United States, and even a lot of the eastern United States. And it's kind of hard to tell the gray from the purple, but there's some lag NSSL mixed in here too. And you also notice that, right, we keep saying the same model names over and over. It's not until you get to 24 hours that you start to see some pinks here in South Dakota and Nebraska, so the lag FE3, and then the FE3 itself down here in Arizona in the North American monsoon region, producing some extreme precipitation at daily periods. So that's how it predicts, it produces extremes, but how well is it actually predicting the extremes? And again, at different thresholds and accumulation intervals. So to define our extreme precipitation for validation, we're going to use annual recurrence intervals. So this is your 1 in 2 year or your 1 in 50 year event. These are based off of what's called NOAA Atlas 14, which is the estimates of these frequencies of occurrence. But Herman and Schumacher in 2016 and 2018 kind of combined Atlas 14. Atlas 14 doesn't exist in the northwestern United States, so they combined Atlas 14 with some older estimates and put it all together in a nice CONUS estimate of these different annual recurrence intervals. So we have our hourly, our 6-hourly, and our 24-hour, 2-year ARI, 10-year ARI, and 50-year ARI. Not surprisingly, right, like the Southeast shows up again as being very, you're not going to have a lot of exceedances here, right? You have to get some pretty extreme precipitation in the Southeast to exceed these values. Whereas in the Western U.S., right, like these values aren't very high. It's dry there, but it's going to be a little bit easier to get values that exceed these. And so this is what we're going to look at for, observed exceedances versus forecast exceedances. For our reference, we're going to use MRMS, so the multi-radar, multi-sensor product, using their PASS2 multi-sensor QPE. That's their, should theoretically be their highest quality. And then going to look at not just point, but these are high-resolution models. We don't expect them to put things in the right place at the right time. It's a very hard job. So we're going to look at a radius as well. A lot of studies look at 40-kilometer radiuses, and when we were thinking about this and coming up with the design of this project, and I was sitting in my office in Boulder, and I was kind of thinking like what is this is America, what is 40 kilometers? Where, right? Where does that take me? And so I pulled up Google Maps and I put a pin on my office and I drew a line that was 40 kilometers long, and that put me like 2 watersheds away. So that's what I'm showing here, right? Is that here, if this is Boulder, if I had a 40-kilometer radius, a storm that I was calling like a good forecast could, and this is extreme precipitation, right? Extreme precipitation, flooding, impacts could be in any of 6 different watersheds at that point. So you need to balance, right, between I want to have my forecast and tell me where my impacts are going to be to the best of my ability, but I also know that this model is not going to be perfect. I need to give it a little bit of leeway. So we settled on 25 kilometers, which is this yellow circle here. So you can see, that still overlaps 3 different watersheds, but it's a lot closer. Obviously, if my point that I was interested were like, say, right there, there's no way you're not going to put a storm in the wrong watershed, but 25 kilometers is a little bit closer than that 40 kilometers. Okay, so the first thing we're going to look at is the ability to forecast extreme precipitation with the appropriate frequency. So I'm just going to show the 2-year, 6-hour ARI here. These maps look fairly similar for all of the other thresholds and all of the other accumulation periods. This one is nice because it's 2 years, so it happens a little bit more frequently. So you can see here's the number of observed occurrences, and as I mentioned, you'll note that most of them are in the Mountain West. There are a few kind of in the Ohio River Valley here. They're a little bit more sporadic. And then you'll note that the number of times any one of those models in the HRF predicts it, it's a lot more than is observed, right? But the spatial distribution is about right? So it's centered kind of in the Mountain West and sort of in the Ohio River Valley. It goes a little bit kind of overboard, along the eastern seaboard, but the spatial distribution is kind of there. The number of times you get 2 models to forecast is actually a lot better, right? This looks a lot more like this. And that's true, like I said, for all of the accumulation periods and all of the ARIs, is that the number of times you get 2 models to forecast it looks a lot like climatology. And then of course, maybe not surprisingly, extremes, they're kind of hard to predict, so it gets really hard to get, you can get 3 models to forecast, 4 to agree on an ARI exceedance pretty easily. Once you get to 5, 6, right, these start getting pretty much 0 most of the time. Again, except for Hurricane Hillary, where things were pretty seemingly predictable. At least the models seemed to agree pretty well on what they thought was going to happen. Without Hurricane Hillary, this would have cut off. Like by the time you hit 7, you'd be like looking for little pixels of 7 models forecasting. It doesn't happen very often. So looking next at sort of the quality of the forecast, and for those of you who are not Ensemble model validation experts, so this is a reliability diagram. And so what we have on the x-axis is the number of models forecasting. Because there are 10 models in the Ensemble, if you multiply this number by 10, that's your forecast probability. And then on the y-axis, we have the probability of an observation given that number of models forecast. So we have your 1-to-1 line, right? So ideally, if 4 models predict that this is going to happen, you have a 40% forecast probability. 40% of the time, you will actually observe an ARI exceedance. So if you're above this 1-to-1 line, that means we're observing it more often than it's predicted, and we're under-predicting. And if we're down here in this orange quadrant, below the 1-to-1 line, the models are overconfident. They really think this is going to happen, and it is not observed with the same frequency. So here is looking over the entire CONUS. So our blue lines here are our point validation. Not surprisingly, they are not great. And our orange lines are our 25-kilometer radius. And as we get with less saturated lines, so the solid line is hourly, the dashed line is 6 hourly, and the dotted line is 24 hourly forecasts. And so what's kind of neat here is so to exceed a 2-year ARI, we're actually doing pretty well. At a 25-kilometer radius at 1 hour, the model's fairly reliable, up to about 50 to 60% probability of occurrence. And we're kind of underconfident in our daily and our 6 hourly, and then it sort of goes to an overconfident. But again, recall the maps I just showed, this doesn't happen very often. This is pretty noisy. There's not a lot of data points to fit into that 7 to 10 model agreement kind of space. Our point forecasts completely all overconfident no matter what you do. When you go to a 10-year ARI, now we're looking pretty good at 6 hourly forecasts. And then interestingly, right, so we go hourly, 6 hourly daily, hourly, 6 hourly daily. When you get to the 50-year ARI, now our daily forecasts are pretty good. And so it's now hourly, daily, 6 hourly. So as you go from a 2-year ARI to a 50-year ARI, you get better quality with longer accumulation periods. This is not terribly surprising, but it was actually good to see how reliable it was at that 25-kilometer radius. Now I mentioned that again we're looking at extremes. They are rare, and so that was the CONUS. If we go back and we look at our regions, you'll see now that our 25-kilometer radius, right, is mostly under predicting. In most of the country, these point forecasts aren't bad. They're within about 10% of being reliable, right? Except for the West Coast, where Hurricane Hillary occurred and is driving all of that previous, right? This is a 50-year ARI, super, super rare events that, this is really driving those CONUS-wide statistics that I showed in the previous slide. Okay, so how do the individual members now contribute to these forecasts of extreme precipitation? Okay, so going back to our 2-year, 6-hour ARI, right, here are our observations. Now this is the number of times each of the different models forecasts. So we have the ARW, the FV3, the NSSL, the HER, and the NAM, and then their lags right next to them. If you remember from those maps I showed earlier, who's the most frequent maximum member for a given time? It was the NSSL and the NAM in the mountains, right? And you can see right here the NSSL is really, really overdoing it, particularly sort of in the mountains of Colorado. Same thing with the NAM, really, a lot more frequently than observed, predicting these 2-year, 6-hour ARI exceedances. Their lag members are a little bit better than they are. You can see that the FV3 actually kind of looks pretty good. It's overdoing it quite a bit in the eastern U.S., but it looks pretty good in the western U.S. The ARW and the HER, they're a little bit too low. They're not quite predicting with the right frequency compared to the number of observed occurrences. So the next thing I'm going to show to kind of see how each of these individual members contribute and how each of these individual members have different biases and different qualities. We're going to use rubber performance diagrams. So on the x-axis, we have success ratio, which is 1 minus the false alarm ratio. So a low false alarm ratio is going to put you over here, farther out towards 1 on the x-axis. On the y-axis, we have probability of detection. Across the top and the right axis, this is our frequency bias, and that's going to be in these diagonal dashed lines of constant frequency bias. So are we predicting more often or less often than it is observed? And then these curved lines are critical success index constant. And so ideally, a really good forecast is going to be up here in this top right quadrant of the figure, where you have good CSI, you have close to 1 frequency bias, high probability of detection, low false alarm ratio. You could have, say, this guy right here, right? It's got a pretty low, it's like a 50% bias, but it's got a low false alarm ratio, a high success ratio. So this one here, right, is, if it predicts it, it's probably going to happen, but it doesn't predict it often enough. On the other side of that, we have something like this, right, where you have a really high probability of detection, but a really high false alarm rate. So it's predicting it, I call it the boy who cried wolf, right? It's predicting it all the time, but it only happens part of the time. And then you can have something like this, right, where it's right on that 1 frequency bias. It's predicting it with the right frequency. It's just not putting it in the right place at the right time. So it's got a really high, a low POD and a high false alarm rate. And so that's how we'll interpret some of these going forward. So this is all for the 2-year ARI at our 3 durations. And to just sort of walk you through here, right, I decided to look at a million different things, because that seemed like a good idea at the time. So our point validation statistics are going to be in the circles, and our 25-kilometer radius is in the squares. Filled symbols are the non-lagged models, and the open symbols are the lagged members. And then you'll want to kind of keep an eye. Sometimes the axes sort of change because of kind of that low skill that we sometimes get. And for this, right, for the 2-year ARI, it's kind of interesting, like our 25-kilometer radius at 1 hour has like similar skill to our point at 6 hour, right? So we're hovering kind of around that 0.1 POD, just around 0.1, similar bias, the success ratio at 1 hour is a little higher, but our POD is about the same for the point at 6 hour as it is for the 1 hour 25-kilometer radius. You'll notice that things are kind of clumped together, and then there's this red square, so the HER, and this purple square, which is the NAM, and you'll notice that they're there at 6 hours and at 24 hours, and this is pretty consistent over all of the accumulation periods and all of the ARIs. That the HER has the best sort of false alarm ratio. It's got a low false alarm ratio, but a low bias. It's not predicting often enough. But when it does predict, you're probably gonna have something happen. Versus the NAM, which is got the highest probability of detection, but kind of a meh success ratio. You'll notice that as we go from hourly rainfall to 6 hourly rainfall to 24 hourly rainfall, not surprisingly, our skill increases each time you get a longer accumulation period. That's partially because that allows you to sort of average out timing errors in the models. You'll also notice that our lagged members, so our open symbols, right, they're all lower skill than their corresponding non-lagged members. So probably data assimilation helping out with giving it some information about more recent updates to what's actually happening, and those taking that forward and having more skill. And then you'll notice, here's the FV3 down here, hanging out with all the lagged members. Unfortunately, it's got a really great frequency bias, right? We showed in that map that the climatology from the FE3 looks a lot like the climatology from the observations. It's predicting it with the right frequency, it's just not putting it in the right place at the right time. So this now is looking at so just 6 hourly rainfall, but the 3 different accumulation periods, or annual recurrence intervals. And so, maybe not surprisingly here, is that as you get to more and more rare events, now our skill goes down. So we still have the HR and the NAM, HR and the NAM, HR and the NAM. You can actually see the lag HR here at the 50-year ARI start to sneak up and hang out with some of the non-lagged members and have better skill there. And you'll also notice, I didn't put this out in the last slide, but you'll start to see sort of the HR and the ARW hang out together a little bit. They'll have similar skill in a lot of these different plots, and the same thing with the NSSL and the NAM. They'll have similar skill and similar contributions to the extreme precipitation. But similarly, right, the lagged members are not as skillful as the non-lagged. HR with the high success ratio, NAM with the high POD, FE3 with the great bias, but not great at putting things in the right place at the right time. And so, higher accumulation period, better skill, more rare event, less skill. I won't dwell on this for terribly long, so because we had our regions, I didn't want to show you a million Robber diagrams for all of our different regions and all of the different models. I call this the flannel shirt plot. It reminds me of a flannel shirt. So this is just the ratio of the number of times that the models forecast to the number of observations. We have our 6 regions along the y-axis and our 10 models along the x-axis. And you can, things that really stand out are like the bottom 3 rows are usually all green, right? So we're over-predicting in the Northeast, the Midwest, and the Southeast. And so this is the 2-year ARI on the top row and the 50-year ARI on the bottom row. And you can see that for both of those ARIs, as you go up in accumulation period, right, these greens sort of get lighter as you go up in accumulation period. So we're getting better frequency bias as we go up in accumulation period. For the Great Plains, Mountain West, and West Coast, things are a little bit more variable, right? Some of the models are under-predicting, some of the models are over-predicting. But you'll notice again that as you go from shorter accumulation periods to longer accumulation periods, the colors sort of get a little bit more muted. So our frequency biases, whether it's too many, over-predicting, it's over-predicting less, or under-predicting less as you go to higher and higher accumulation periods. So just to wrap up, we're getting to that 45-minute point. So the probable maximum precipitation, we're going to update those as part of the Bipartisan Infrastructure Law, and we're going to replace our outdated, terrible deterministic estimates with state-of-the-science, robust estimates that account for uncertainty and account for climate change. The 2-year study that's going to be completed in 2024 is going to give us those recommendations as to how to really move forward to develop something that is CONUS-wide and not more piecemeal like the thing that we did previously. And as I mentioned, we're going to update these more often than every 50 years going forward. And so meanwhile, what we're focusing on is really exploring what we have available to us now and exploring what some of the experimental models are doing, focusing on different dynamical cores and ensemble model systems. And then from the HREF, right, so what does extreme precipitation look like in the HREF? So the highest precip maxima, not surprisingly, are in the Gulf and Atlantic coasts and up into the Mississippi Valley. And the ensemble maxima really varies with your accumulation interval and your regions. How well does the HREF predict that extreme precipitation? CONUS-wide, if you're looking at 25-kilometer radius, we're pretty good. If it tells you it's going to happen 50 to 60% forecast probability, 50 to 60% of the time it's going to be observed. But those you're looking CONUS-wide, right, the point forecasts were consistently overconfident. When you looked at different regions, though, that told quite a different story. Forecast skill increases with accumulation interval, but decreases with the rarity of the event. And then how do the individual members contribute? So the HR and the NAM really stand out as having consistently high success ratios and consistently high probability of detection. The non-lag members really generally produce more skillful forecasts than the lag members. There are some exceptions to that. You do see a few of the lag members, mostly the HER and the lag NAM, sometimes jump up and join the non-lagged members as being pretty skillful. But for the most part, those non-lag members are better than the lag members. The FP3, which is our going forward supposed to be new dynamical core in the unified forecast system, it's doing the right thing sort of as, with frequency of extremes, but it's not putting them in the right place at the right time. Most of the models overpredict the frequency of occurrence of extremes in the eastern US, and there's more variability as to which models, some of them overpredict, some of them underpredict west of the Mississippi River, but the biases generally decrease with accumulation interval. And then as I pointed out multiple times, like even with 3 summers of data, we're looking at rare events, the number of samples that we have is really small. And so one event can really, change your statistics going forward, and so this really highlights some of the challenges going forward of working in this realm of rare and extreme weather. And that is all I have. As a fire hose of information.
Great. Students, what questions do you got for Janice?
Thanks. Do you have a reason why you didn't include wintertime precip and how important it is on the West Coast, and would that change your statistics?
Yes, it would change my statistics. We did not include it currently because, we can look at that later. We do a lot of work actually in my lab looking at streams on the West Coast. As I mentioned, I started, with the AQPI project. When we started this project, it's already, so very much data to crank through just 3 summers worth it already takes me like a week to run through that. So yeah, so we can go back and look at that, but we were just sort of focused on the eastern, the western US is in the maps, but yeah, the eastern US was kind of the focus, and then Hillary happened and threw off all my statistics.
Other questions from students? All right, we'll open it up while you guys are thinking. Dave, go ahead.
So you mentioned a few times that one individual event can really shift your statistics. So I know it's a lot of data to mine through, but would it be worthwhile to maybe broadly categorize some things? Is this from an atmospheric river event, a synoptic frontal event, warm frontal event, or is it a tropical cyclone, to help really parse out, which models are doing well for, I guess, specific situations and their experience of the data?
Yeah, that ideally we would do that. That's kind of where I was sort of going just by divvying things out into regional statistics, was to try to capture some of that. Obviously, if you read different papers, they do the regions differently. This was just a very easy, line of longitude kind of thing. But yeah, it would be ideal to actually go through and, use the storm characteristics, identify individual events, the storm that it came from, categorize those, and then redo this. But I only have till June when the NASEM stuff comes out.
Good idea.
Do you have any idea if the scale in the HREF changes from early summer to late summer? I know you just used the full summer data, so.
I'm trying to think, so my colleague Diana, in hers, she's looking at the means in the HREF, but she has been running her statistics June, July, August. I don't think she sees, no, I take that back. I do think she did see a little bit of a difference late summer versus early summer. And I think she did also try, wanted to kind of attributed that to ramping up of hurricane season. Yeah. If you're going to AMS, you can go see her talk. all of those questions, right? So when I highlighted the questions earlier, and I had that Diana was doing some and Sarah was doing those will all be presented at AMS this year if you're going and you're interested.
And then a follow-up is, at least not for that 24-hour time scale, but do you have any idea of a diurnal component to this forecast scale?
Yes. That is also in some of Diana's work, and she is seeing a little bit of a diurnal component to the skill.
Dan?
Thanks for the talk, that was very interesting. In thinking about some of these, extreme precipitation maybe that these events are just purely unpredictable on the kinds of scales that they actually occur. Is there a way of parsing out like, the difference there between the models not getting the forecast because the models have problems versus models not getting the forecast just because even if they perfectly got the large scale, there's still just random variability that you're never going to resolve.
Yeah, this is, that we've had a lot of discussions about this, actually, that like, you know, it'd be sort of the same thing, right? You'd have to identify different cases and did it do well, did it do poorly, okay, why, yeah, it's like a lot more digging, but it would be super interesting to be able to do that. And like I sort of mentioned, like, you very rarely, even with 3 years of data, right, you don't usually get more than 6 models to agree on something. They thought Hurricane Hillary was very predictable, but like monsoonal precipitation is a lot more challenging. So yeah, it'd be a lot more, you know, we only have till June, unfortunately, but it's something we've definitely talked about in our group, that like it would be really nice to be able to dig in and find out which things are actually, you know, predictable versus not.
I guess what I'm thinking there is if, you know, in case of monsoon precipitation, if you're, you know, if that's never predictable, then maybe that informs the approach you take differently.
Right,
You know,
right.
in terms of using more of a probabilistic approach or something instead.
Right.
It seems like I like the fact that you divided that into regions because you can kind of look at, I mean, you know that's West
Yeah.
Coast, you're not dealing with monsoonal precipitation, but you can kind of like parse that stuff.
Yeah. My West Coast domain actually does a little bit have, I think, some of like western Arizona that does sometimes see a little bit of that monsoonal precipitation. But yeah, you're right. Like, and they're not, in some of my experience, I've seen the models like nail some monsoon precipitation, like some extreme precipitation out of the monsoons. Like just this past summer, some of these models like nailed it on a couple of the storms, and then on a couple of them, you know, they had nothing. So there might even be some, you know, why is this one monsoonal storm so much more predictable than this one?
Yes, I have a question about, it's interesting to me that some of the models group together in skill, and so
Yeah.
I don't know how easy it is to go back to the slide where you talk about the different parameterization schemes. And the first thing I was wondering, and it kind of gets a little bit to some of these questions, like, can some of them get the general idea right, but they just can't, within that, produce high enough precipitation efficiency or
Right.
something? And is it tied to the different parameterization schemes? So like, what would you say? It was like the HER and...
Yeah, so the HER had a good success ratio but a low bias.
And it kind of grouped with, was the
And
ARW.
yeah, the ARW.
And so it's interesting then that they don't really have a lot of similarities, at least in their
They're using the same initial
microphysics.
conditions.
Yeah. Okay.
Yeah.
So they're both wrapped. So that's maybe what it is.
It could
Whereas
be
the
that.
NSSL and the NAM use the same initial conditions.
Yeah.
So that would probably explain the
NSSL and
grouping
NAM are using the same planetary boundary layer too.
rather than the microphysics. So
Right.
it was interesting to me that the microphysics didn't group together. So it's
Right.
way beyond just
That's actually, that's like a
producing.
really good point, and that's something that I have not even thought about looking at and being like, oh, then why? Yeah, that's actually a really good question.
Okay, yeah, that was different when I thought that's really interesting.
Right, no, that is really
Yeah.
interesting.
Other questions? Yeah, Dave.
Do you take, I guess, occurrence based off a previous event into account? So if you had many days of maybe not extreme precipitation, followed by, many days of also not extreme precipitation that maybe over a few weeks could lead up to something that could be catastrophic, is that counted into this, or no?
This is just, every day at 0 is either in the model. Yeah. And we've talked about too, like, I only look at 0Z, there's a 12Z run, right? Like, let's talk about the diurnal cycle, right? Is there a diurnal component to what's being assimilated at 0 versus 12Z that has impact on skill? But like I said, 3 accumulation intervals, 3 ARIs, point versus radius, 6 regions. it was a lot to crank through. And I mean, we could do this, yeah. I can make like the next 3 years of my job be digging into the HRF, but the Rufus Ensemble is gonna take over in 2025, it might be now.
I have another question, because like, this is something we think about like on a much smaller and shorter time scale of like, what's truth, right? And so, it's a really hard question. And so, I know you're using that database, and you have MRMS, and what really stood out to me was how much models were over-predicting in the mountains. But how much do you trust the reliable ground-based data set, relying on radar and others in the mountains? Do you think it's...
I think it's better in the summer than it would be in the winter.
Yes.
Just because it's more convective, it's taller, there's a chance that the radar might catch it.
Yep.
But yeah, it's, well, and the other thing that I didn't mention is that MRMS at its native is 1 kilometer.
Yep.
I course it to 3 kilometers, which is also gonna sort of wash out some of the extremes in the MRMS. So it could be that part of the overprediction from the models is actually like just the MRMS being coarse and not having the extremes
Okay.
that it would have had.
Yeah, I was kind of curious why like those models in particular are like just blowing things up over the mountains all the time. And so if it was the observational data set, you would think that all the models would show that. So maybe that's not it, but I was just wondering, yeah, like how to maybe explain that overprediction.
Yeah.
Yeah.
And like my colleagues at the WPC, they actually really like the NAM. They love the NAM.
Huh.
They kind of like that like high probability of detection, but like, you know, middle of the pack false alarm ratio, like the NAM's gonna get it. Whereas the HER, you know, like I said, the HER is gonna maybe not get it, but if it tells you it's gonna happen, you're more likely to see it.
Yeah. Other questions? All right, she'll be sticking around if you wanted to come up and talk to her separately about the research or her career path. And thanks again for
Thanks for having me.